I hope everybody sort of enjoyed their spring break and are having a happy coronavirus-free day. As you have no doubt already heard, we will be doing online instruction from here to the end of the semester, and hopefully next fall we can all return to a normal life. Well, hopefully before then. So I will be doing these tutorials and posting them so that you can look at them. They will be in sections because the files are too large for just one file per chapter. So the chapters will be broken down. I'll explain all that later. Today's and all of the tutorials are based off of McKnight's Physical Geography and Landscape Appreciation, which is put out by Pearson Publishing. Hopefully that covers me so I don't get in trouble for plagiarism and nobody gets all wound up. All right, we're going to start with chapter 12. Now, I know you took some notes in class on the beginning of this chapter, but because of the way the school semester kind of ended, I want to make sure I start at the beginning of chapter 12. Chapter 11, of course, you already have the notes on it. So soils. These are some of the topics we're going to go over. You can read through them. They will be broken down into two different sections or tutorials. All right, soil and regolith. The thin layer on top of the Earth's crust, which is about 15 centimeters deep. Now, this does not mean it's 15 centimeters deep everywhere across our planet. In some places, it's deeper. Some places, it's shallower. You get out in the desert, and the Namibia Desert, for instance, which is like total bedrock and all the sand is piled up in one spot, you're not going to find any soil at all. All you're going to find is hard bedrock. And then you can go out to western Oklahoma and you may find soils that are 3 meters deep. So again, it all depends on where you're at. Some soils are deeper in one place and shallower in another. It's kind of like our atmospheric processes and our global conveyor belt that we've talked about, in which, yes, it's warmer at the equator, cooler at the poles, but when it comes to the average across the Earth, it all kind of equals out. A complex combination of minerals, organisms, gases, liquids, etc. And we're going to beat this topic to death. Please remember, all soils are 50% pore space, and in that pore space is atmospheric air and water. And of course, water and air have all the components or gases that are in the air and water get trapped in the soils. So it's this intricate interstices between all of the different spheres. It nurtures life. We got to have soil to grow food. You can't grow trees, food, or anything else. And if you don't have no trees and food and what have you have no animals. So it nurtures life. Again, the fundamental interface between the four spheres, because of where the gases get trapped and how the biosphere works with the lithosphere works with the atmosphere, and the hydrosphere. Regolith is the inorganic material that results from rock weathering. Inorganic, okay? So not necessarily the very top soil is sediment, and sediment can be on top. So I know the picture, if you look to the right or up above here, to the right, it says regolith there on the side, and that regolith, of course, shows it going all the way to the top, but it's the inorganic portion, so it's the sediment that's in there, okay? The top layer of regolith is different in the amount of biochemical weathering, because if it's buried, it's not being weathered nearly as fast or as quickly as the upper levels. Surface of the lithosphere always represented by soil. Depends on where you're at. I don't want to say always represented by soil because there are places with zero soil. It's just sediment. Soil often recognized by color, which is true. Here in Oklahoma, our soil is red. And a lot of people say, oh, it's red because of clay. No. Clay can be any color. There are blue clays, black clays, red clays. There are all colors of clay. Our soil is red because of the iron. Our sediment, or source of sediment, comes from the Rocky Mountains to the west of us. And there's a lot of iron there. And so that iron is what helps turn our dirt red. Depth is also important, but it is only obvious when exposed through excavation. And that's what I do. I go out, I cut my trenches. Or I auger. It depends. Sometimes I got to go 12 feet down, and I'm not digging a 12-foot pit. I'll do an auger instead. But That's when you find these subsurface soils or even paleo soils that have been covered up. I have a 22,000-year-old paleo soil in Eagle City, Oklahoma. So depth is also important, but a lot of times we can't see the intricate parts or the what we call pediogenesis, which is the structure of the soils and their horizons, unless we excavate and we clear those up. All right, soil forming factors. First one is the geologic factor. Source of rock fragments of soil is what we call parent material. Sand, silt, clay. Nature of the parent material influences the soil characteristics. Does it have iron? Does it have calcium carbonates? Does it have limestone? It all depends. Young soils are very reflective of the rock sediments from which they result. And that's because you start out with sediment. And then that sediment will pile up somewhere. If there's enough moisture, maybe some plants will take root. And sediment doesn't become soil until it starts getting broken down by plant roots, burrowing animals, and especially worms. Okay, so sediment is sediment until it becomes stabilized, and then it starts turning to soil. That's the geologic factor, and it takes time. The climate factor, temperature and moisture, significant to soil formation. All right, so here's the thing. If you have a soil that is disturbed, eroded, lots of flooding and stuff, every time that it's eroded, weathered away, and deposited somewhere else, that clock resets. That sediment is broken back down, okay, to its basic elements. However, if you leave it alone and it stabilizes and it builds up and it builds up and it builds up, then you get a stable soil. You get a well-developed soil. So the climatic factor, temperature and moisture. Got to have the right temperature, got to have the right moisture. If you have moisture, not too much, but the right amount of moisture, and it's hot, soils will develop quicker. Chemical and biological processes accelerated by high temperatures and moisture. There we go. Next are the soil forming factors. Topographic. Again, if you're up on the side of a mountain, you look at the top picture right here, you got thin soil. It's on a slope. All of it gets washed down to the bottom. That's where your thick soils are. That's where you get depth. So slope and drainage are significant. And the lower of the top of the bottom of the soil. Again, mountains erode down. So you constantly have a sediment load or a source of sediment that is constantly being deposited down where your soils is and then being mixed in with those, okay? And then biological factors. All soils contain some quantity of living organisms. If you want a good garden, find a place with worms. I'm telling you, I got people that come by every year taking pictures of my garden. My okra gets to about 14 foot tall. Tomato plants get sometimes, 10, 11 foot tall. I know you think, oh, no. If you got good soil, it'll grow. And guess what? I got good soil. How do I find it? Find the worms. Worms aerate. They leave excretions. They turn those nitrites into nitrates. So they're excellent, an excellent source of bacteria and everything else. That's what creates soil. So anyway, here we got our little prairie dog city, and of course prairie dogs are bioturbating. They're getting down there and they're mixing it all up. Okay. All soils contain some quantity of living organisms, plants, and animals' contributions to soil's development. Again, roots, everything else. And again, prairie dogs and stuff, that is called bioturbation. Okay, biological, and they're mixing it. Biological factors continued here. Earthworms are the most important. Innumerable tunnels mixed by water, crumbly surface, digestive actions increase porosity and resist raindrops, so it helps with flooding, lessens erosion. Cast excreted by earthworms, they leave a cast which leaves like a burrow that allows other things to go into those burrows and be absorbed by the soil and mix with the soil. Rearrange material in the soil, and again that nitrification promoted, nitrites to nitrates, and nitrates are fertilizer. And microorganisms enhance biological decay. So we mix all these things in, that's what creates soil. Last but not least is time factor. Soil processes are very slow. If you end up with a flooding event, boom, it's gone. Okay, you can't just rebuild it overnight. Soil takes time. You have to, keep it buried. You got to keep it protected. You got to have the worms and this and that. Okay, if you just constantly take and mess with it and erode it, you're never going to get a good, well-developed soil. And we'll talk about what development is here in a little bit. Length of time needed depends on the parent material and environmental characteristics. Soil degradation or erosion can occur in only a few years. In the cases of hurricanes or something, a few minutes. From a human perception of time, it's a non-renewable resource. All right, we're going to skip this slide. You really don't need it. Just know that clay absorbs water. There's no porosity to it, which is why you go up north to Kansas, Iowa, Nebraska. They have basements on their houses. We don't, because of shrink swell. So half the volume of, well, we do need to look at this. Half of the volume of an average soil is sand or silt, which means the other 50% is clay. Okay? Clay has colloidal size, and clay attracts cations. It's water attracting negatives and positives. Okay? All right, here we go. Organic matter. If you'll look, 50%, again, pore space. We're going to beat that topic to death. The other 50% is mineral matter, and 5% of that 50% is organic. Living organisms, dead organisms, completely decomposed organisms, it's all mixed in. Rearranged and aerate soil and yield nutrients through waste products. And then we have some other things here. Litter. What is litter? Litter is the leaves, twigs, or other dead plants parts on the soil surface. Okay? They're not intertwined. They're not mixed in. Okay? And then humus, which is a black gelatinous organic matter that results from decomposed residues, usually swampy areas or up in the higher latitudes near the Arctic where you got bogs and stuff. Okay. Some other components. Soil air. Half the volume of average soil is pore space. Spaces provide interstices among soil particles. It allows them to kind of bind and bond together. The pores are filled half with air, half with water. All right, soil water. There are different types of soil water here, 4 types. So we have rainfall, snowfall, groundwater through capillary action. Remember, capillary means moving up, okay? So here's our 4 types. 1, we have gravitational water. Gravity pulls it down. We have capillary water, roots and stuff. It works its way up through the roots and stuff, all right? So gravitational, infiltration from above falls down via gravity. Capillary water, moisture that is held on soil particle surfaces by surface tension. And then I want you to look at this eluviation and illuviation, one with an E, one with an I. Eluviation is where minerals and what have you are literally leached out of that layer and transported into the layer below. So eluviation is a leached soil. It has no minerals. It has no characteristics really to it. The illuviation is where everything ends up. So from eluviation into illuviation, and we'll see that again on the next slide. One of our other 4 types, this is the 3rd type, hygroscopic water, thin film of moisture bond to soil particles by adhesion. So one on roots, this is soil particles. And then the least common of all of them, or the rarest, is combined water, held in chemical combination with soil minerals. You might want to remember that one. Now, field capacity wilting point, I'm not going to get into that right now. We will set up a time to do a review for the lab final, and we will go over that at that time. Leaching, water carrying nutrients and minerals down in a soil, okay, which goes with the word below that, eluviation. So leaching means it's void of minerals, it's void of nutrients, everything's been washed out. A lot of times this is where your swamps, again, or your high latitudes, bogs and stuff, you'll find these. Usually associated with what we call the E horizon, which we will see in the next tutorial. Illuviation is where everything ends up. So it's transported out of one or washed out of one and into another. All right, soil water budget. Amount of water added by percolation snowmelt is diminished by evapotranspiration. Depends on the time of year, okay? So in general, cool temperatures mean less evapotranspiration, and that's just because we don't have direct sunlight. Remember, you can become more dehydrated in the winter than you can the summer, because when you're cool, you don't feel like you're losing moisture, even though the wind and the cold is sucking that moisture out of you. The other part of that is plants are dormant during the winter. So of course there's less evapotranspiration. So we don't see it. Plants are dormant, we don't have direct sunlight, and we don't have the heat. Okay? All right, here's our soil properties. This is where we get into pedogenic or development. Okay? So anyway, first things first, we went over this in class, but make sure you understand, always do sand and clay. Don't worry about the silt because then you're trying to cross-connect dots and you mess up. Make sure you look at your percentages. It's real simple. If you have 400 grams out of 1,000, you've got 40%. If you've got 200 grams out of 1,000, you've got 20%. If you've got 20 grams out of 100, you got 20%. So brush up. You will need that for the lab test. However, what happens if somebody says, oh, you got 500 grams? Whoa, wait a minute, 500 grams? What am I supposed to do now? That's not a nice 100 or 1,000. Just double it, okay? So if I've got 200 grams of 500 total, I double it, okay? 500 times 2 is 1,000. 200 times 2 is 400. 400 goes into 1,000, 40%. Very simple, very easy. Just don't get too wound up on it. Just taking one step at a time. So let's say I've got 20% sand and 40% clay. Okay, so what do I do here? Well, let me turn on my little pen. I've got 20%, and I'm going to try and draw here, 20% right there, sand. And then I take that blue line and I just follow it up till I hit my 40% clay. It is that simple. Oh, I'm right on a boundary there. Didn't mean to. I just picked some numbers and went with it. So I'm right on that. I could have a clay, a silty clay loam, or clay loam. On your test, it'll be a little bit better than that. So it'll probably be 41% or something like that. So anyway, just make sure you know how to do it. Again, you're not going to get a pretty triangle like this. It's nice, easy to read. But it will be close to a line. The X marks the spot will be close to a line. So anyway, make sure you know how to do your percents. Over here on the right-hand side, these are development techniques. So when you first have sediment, it's first starting to become a soil, it's spheroidal, granular, or crumbly. Otherwise, you take it in your hands, rub it together, and it breaks apart. Plate-like, E-horizons, those are the ones that are leached, high latitudes and swampy areas. All right, rainforests are also leached out, okay? Lots of rain. Usually they're white in color, those soils, and they have these platy or flattened beds. The ones we have here in Oklahoma for the most part are these B horizons, all right? The block-like, the angular blocky, the subangular blocky. I run across those all the time. And if you've got a really well-developed buried subsoil, you may end up with a prism-like. That's one that it hasn't been touched in forever. It's been sitting there, and by golly, it's built up to almost rock. Even your angular blocky and subangular blocky usually have some caliche, which is white calcium carbonate nodules mixed in with it. It's still hard. Don't get me wrong. Summertime, you're using a pick. You're not using a shovel that often. You're using a pick. This is just a table here that kind of shows all the different message. If you remember in lab, you had to shake out sand, silt, and clay. This shows you all the different sizes of the grains. And I do have all these screens, so I literally have to screen everything. But I want you to just notice the clay one. 0.002 micrometers. Folks, you can't see clay. Remember, I told you to get clay out of stuff because the clay actually adheres to sand and silt. To get it out, you've got to put it in water, mix it up, wait 50 minutes, the sand and silt will settle to the bottom, and then you pour the dissolved clay off. And you continue that until your water is clear and all the clay has been poured off. Okay? You can't see clay. Clay is microscopic. All right, particles aggregate into PEDs. What's a PED? Well, a PED, let me do my little marker here. A PED, again, it's sediment that's starting to get developed. Kind of looks like that. okay? And it's when more than one grain of sediment starts coalescing together. So you have individual grains, and then as they start to coalesce, they make these little beds, these little, what do I want to call it, just little, they got little pores in them, but they start coalescing, right? And then the more they coalesce, then they start turning into that subangular blocking and angular blocking. They start, coalescing more and getting larger and larger and larger, okay? Porosity, soil's capacity to hold water. Again, 50% of all soil is pore space filled with air and water. Permeability, the ability of water to move through a soil. Sand, silt. Clay absorbs, okay? Clay absorbs water. All right, and soil chemistry here. Again, we're not going to get into cation exchange. We know clay absorbs water. I want you to look at the pH scale because you need to know that an acid has a baseline of 1 and base is 14, okay? So acid is a 1, base is 14, and in the middle there we have our fertile agricultural soils, which are 7, neutral, okay? So you need to remember that for the test, okay? This is the end of the first tutorial on this particular chapter. We will pick this up again with the next tutorial. So anyway, I will see you back in a few minutes. Goodbye.